Sir, we are live, sir. Please start.
Okay. Let's see. Okay, so this is just hold on. First I need to share. Okay, is it visible now?
Yes, sir. I can see, sir. Thank you.
So will it start now or so?
Yes, sir. We are live, sir.
Okay, great. Thank you. So greetings to one and all. I would like to thank NPTEL team for giving this opportunity to share my experiences. We at ANSYS make our living by solving industry problem using simulation tools and processes. My name is Lalan, and currently I lead a team of experts supporting simulation activities for various aerospace systems. In today's presentation, I would like to discuss how we can use the integrated mission modeling simulation approach to solve the urban air mobility problem. First of all, the question arises, why we are talking about the urban air mobility. The image is taken near Silk Board in Bangalore, early in 2021, during the pandemic. And this is a very lean traffic for cities like Bangalore. So this brings all of us to take a stock of transportation equity. Equity refers to the fairness with which the impact, benefit, and cost are distributed. Transportation planning and its decision often have significant equity impacts. Transport expenditure represents a major share of household, business, and government expenditures. So it's all together, we need to take a lot of give a lot of importance for this transportation equity. So how we can improve this transportation equity? Can urban air mobility or UAM is an answer? So if you look into the mobility of tomorrow differently, both from long and short distances, package delivery, or human passenger delivery, urban air mobility is a whole new aspect of air transport that offers new opportunities to aviation stakeholders. It is also an opportunity to construct a green and sustainable subsystem, building upon the lesson learned over the decades of aviation, which we have all been experienced through. Urban air mobility involves a completely new type of aircraft. It could be vertical takeoff and landing, which we also call as a VTOL systems, with electric propulsion, integrated engine, and flight controls, a new operational concept, and also because of the autonomy and also very little involvement of the pilot, also you can say the pilotless aircraft. To face these challenges, there is a strong need for efficient development process and tools to meet these safety and airworthiness objectives. So what are the key challenges brings through this urban air mobility, development or the urban air mobility operations? Because of the less pilot involvement and majorly driven by autonomy, three critical challenges we need to take care of. First is the foremost is the safety and security under different environment and harsh conditions. The second, we need to ensure the connectivity between the vehicle and the ground control stations. Those are intact. Those are seamless. There's no disruption and so on. And then the third is that all about the how well we are able to manage their traffic or their flight paths. The company or the people who will solve this problem first will be the the leader in the market. Now this slides gives you or represent the lay of land for the urban mobility system. So let's focus the two types of the vehicle. One is called the manned VTOL, and second is which is the unmanned the vehicle. Manned vehicle can be you can think that it can be used as air taxis, and whereas unmanned can be used as a package delivery. In the manned system, they interact with the ground control for traffic and trajectory information. They do have a flight computer display for the flight information. The unmanned system obviously needs to interact with the ground station just like the manned vehicle. But in addition, they would also need the ground pilot to feed them with the mission data and also the data to control the flight. Now, these vehicles are software intensive systems, and because of the, especially because of the autonomy. But apart from the software engineer, there are other stakeholders like system engineer, safety engineer, and the system operator. Now, this team needs to collaborate throughout the entire product lifecycle, ensuring that they are all referencing to the same data when they are making a decision or they are making any iteration during their product and operation decisions. And therefore, creating the digital thread using these different digital reference model is the key to success. Example of model-based development process to solve safety and mission analysis are shown on the right side image. System engineer and safety engineers creates the model from the requirement after completing their trade studies and feed these reference model to software engineering team. And software engineering team then finally develop the software model that can be pushed to the hardware to perform model-in-loop simulation. This further can be taken to do a full digital mission verification and validation. In ANSYS, we use a model-based approach for driving this analysis, development, and certification of mission and flight system, as well as the software systems. This model can be validated against a specific mission requirements through digital mission engineering approach with the high fidelity simulation as well. So let's take one use case here. A comprehensive digital demonstrator will showcase the streamlined development process of 2 VTOL aircraft, including critical mission and flight software, 1 manned VTOL aircraft, and there will be another which will follow the VTOL aircraft, which is basically an unmanned VTOL. This focus will be on a specific scenario involving a system failure which could result in catastrophe. The correct system reconfiguration is validated with the mission scenario simulation integrating with the real flight software. And this I've just listed in the 4 steps you can be demonstrated. So the first thing is, let's create the digital mission model. Means actually we need those environment where we need to operate this specific scenario. Here, virtual scenarios has been created within ANSYS SDK tool. The terrain data and the platform can be imported to mimic the actual environment conditions. In this case, we have used Bing or OpenMap to import the actual terrain. You can use any other different format of the terrain which you want to create those environment for. We have 2 vehicles. One is called as a lead, another is a follower vehicle. We have also modeled ground control station. Both vehicle can communicate with the ground control station, which currently you can see here on the video, and these vehicles which you are currently seeing the yellow and gray color nomination, which is the yellow is the lead and the sand color or the blue color is the follower vehicle. So once you complete this digital model for the environment, so what we did in this first step is we brought the terrain data and we imported the 2 vehicle CAD information, which the lead and the follower. Now, once you created the environment now and the platform, now what you need to do is now you need to go ahead with the software generation. So you need to develop those autonomy software where actually this platform will work. Now this slide shows an overview of the different system software components that are included in the mission and system simulation, both for manned, unmanned vehicle system as well as ground station. The manned VTOL flight software receives the input commands from the pilot, from the and communication with VTOL physical model. It transmits the position to ground control station. The station is controlled by an operator. It transmits the data and flight plan to unmanned VTOL to achieve its mission. Now let's focus on the unmanned flights software. There are different software subcomponents from top to bottom. The formation management process processes the traffic data and transmit the lead position with the offset. The flight management software processes the flight plan and compute the target waypoint according to the flight mode. The flight guidance receives a waypoint and calculates the trajectory in between. For example, obstacle avoidance or meeting a certain time requirement or certain desired orientation. The autopilot then executes this trajectory using low-level flight and engine controls. Now, software control codes for various systems generated from ANSYS SCADE tool are used here for mission flight path generation, and then further software in loop is performed for virtual verification. Blue line denote the flight path from the follower vehicle, whereas yellow line denotes the flight path generated for the by the lead lead vehicle. And we are able to see that both the vehicles are following those routes. Let me play this video again, so you can see that the path which, or the flight path which is generated, both the vehicle are able to correctly follow those route which is designated as a mission for these two aircraft. And this flight path is generated by the codes, which is the auto code generator, which ANSYS has a tool called the ANSYS SCADE system, which is one of the the model-based the auto code generator, control software generator, which you are able to see at the right side of the image. So we have the environment, we have the platform, now we have the software. Now let's use this integrated system to look for the operational validation. So let's run this virtual simulation to evaluate vehicle connectivity. We can see that the vehicles are following the flight path, and also it lost some of the places, some the connection or the communication due to the building and the various other the terrain objects. User can also perform various other queries, like which I mentioned on the slide, like the multi-hop communications, sensor coverage. For example, in the military aircraft, if it is part of the military, then it's a more like a signatures. Then it could be terrain masking and so on. So there are various other even in the following the terrain. That itself is one of the very important query which a the mission analyst can look at and perform, that whether we are able to follow the actual terrain and there is a less catastrophic can happen during those delivery or those mission the performance. So in this particular case, we are just focused in this use case. We're just focusing upon those connectivity. So we'll next slides we'll just focus on those connectivity alone. So from that analysis, from that because of this digital mission model analysis, now what we have got, we got the result that yes, connectivity is lost, and there are various, not in once, but there are various scenarios where we lost the connection, the communication. Now what, again, now this information came to the engineers and the set of engineers, and they need to mitigate these issues, right? Because if you lose those line of sight and if you lose those communication, then there's a very bigger problem can happen in the air traffic. So what are the the mitigation? Mitigation can one few of the mitigation in this case actually, which I mentioned, like for example, first thing, they need to ensure that pursuability is maintained, right? So they need to do some kind of a the operation, or do some kind of take some kind of action which can make sure those data or those connectivity which we got lost is taken care of, and we provide the proper coverage. And the second thing is, since we are designing these different system, operator should also be aware about the situation that in case if there is a loss, they should get some kind of alert warning or something, right? So that they don't need to get the overshadowed or overruled about these scenarios. They need to take care that yes, there is a loss of the communication with this particular vehicle, and they need to take the corrective action accordingly. So they need some kind of a alert, information. Easiest thing will be to display some of those information about to the operator. So what next? So now engineers, did the virtual, mission analysis, understood that yes, there is some loss. He also understood that these are the two actions need to be taken care to this. So now they need to go through the iterative design process and make sure these things are issues are mitigated properly. Now, in this case, one of the engineer has taken the one approach that let's add one local sensor into the this particular the vehicle, especially the with the following follower vehicle. So what you were saying is a ANSYS STK UI where engineers are creating those additional sensor and attaching to those vehicles. Again, you can give all those information of those sensor, what is their property, and so on. You can add those specific properties, and you can see about their coverage, and again perform those mission analysis and see whether we are able to provide those coverage or communications or not. So with these local sensors, now again mission analysis was performed and simulated, and actually if you look through these clearly videos that you're saying that there all those coverage has been given quite well, but especially with these local sensors, we are still not solved the problem, especially during the formation joining. But now we are able to provide at least good coverage during the formation flight. So till it is the formation, there is some lag during the initial stage, but otherwise it's giving the proper the coverage during the after the formation flight. So I'm just if you look at the careful. So right now, if you look at those vehicle which is coming here, follower vehicle is waiting and lead vehicle is joining. So till it joins to this same system, so there are some lags. So actually, ideally, follower vehicles should have taken this upfront as soon as the lead vehicle has come in his perspective, in his coverage area. So now it means that there is again we need to run and see what actually again this engineer can come together and look at there is a what next shall we shall we do. And it could be one of the ways is to can we tweak the software to make sure that those things can be mitigated. So the software engineer took this problem and then again he adjusted those controls designed to mitigate this formation joining issues. And with this, at least you can see that he is able to provide the coverage. He has oriented correctly while actually it is coming, and now it is joining, and the formation is able to manage with a very well coverage of the during the entire the flight path or entire mission path which was designed or activated for these people. So now he is able to provide the correct approach to solve this problem using the software. So what we have seen that first we tried with some hardware addition like a sensor addition, but that alone did not solve the problem. So now let's tweak the software and try to improvise the overall goal. So that's where actually we were, in the beginning I was saying that it's not a one of the engineer goals. So it is everything has to work and refer every time to the same model, same data, same software data, same vehicle data, same hardware data, so that there is a there's no mismatch in making while you are taking a decision. Because if the software person would have taken a decision, for example, on the older platform, he would have not achieved because there was already a new hardware was introduced into the old platform. So we have solved that the hardware and software issues. So now that there is one other, so we ensure that the coverage is taken care. So now the next thing is important here is to alert system. Right? So another important information which engineer took that time decision to keep that pilot especially aware about the situation. So we need to add to the system one embedded flight display, which is embedded inside the manned VTOL, so that pilot can monitor the operation from the aircraft and take the right decisions. And this display, we display the the connection status and the position of the member relatively to the piloted the aircraft. So you can create a display where you can give the information about the connection, and also you can give the information about their position, means how far or what is the offset of those between those two vehicles to which is they are flying, so that again they are not in case of a immediate loss of the connection, or there is again a chances of crashing or various other catastrophic damages can happen. Now, so in summary, what we discussed is in essence we developed the flight control software using the SCADE suite, which is, as I said, the auto code certified auto code generator for many the critical software system. And we created a display, which is actually display is coming from the suites, which is SCADE suite, which is SCADE display. So you have a software system which is coming to the SCADE suite, and then SCADE, you have a display which has been developed using the SCADE display, and then here we have used the operation and those verification which we did using the ANSYS STK tool, which is a mission level tool, mission planning tool, which you can in real time you can operate and you can analyze those operational performance of the missiles. So in the summary, I just want to conclude this demo summary with the specific here is that we discussed about the operational understanding, especially challenges, especially if you are looking for the operational understanding. It's a very good that you can create a digital mission model, and you can bring your product and test it for different environmental condition, especially in urban air mobility where the terrains are not very fixed. They will keep on moving. The buildings are erected every time. Cities are, the infrastructures are modifying. So you need to take those on a real time and do quick validation and verification of the operation to see whether we are able to meet those, the mission for either as a, the manned taxi or a, the complete autonomous vehicle or a together, all how actually it can be operated. If you, especially for the automation, autonomy of the aircraft, you need to develop a safety critical software. If again somebody develops a software, then it has the process of the various the debugging and then testing and then getting the certification. So it takes its own time, but in ANSYS we usually use our tool Skate Suite, which is a certified by FAA, many of the standards, and it's auto code generated. So if we create those model based diagram, and from there we develop these those controls software, which is already certified. So we usually save a lot of time during those specific to the software debugging and also testing, and especially going for certification. And then if anyone who is have this the environment model, you have software model, then you can easily perform this the operation validation, because you may have the product which is a very very good, very working very well in its own way, but when it is going on the real the environment, whether it is able to operate, because this especially we are looking at urban air mobility, which is a low height flight. So it's a very important that we have taken the operations and validated against the the current the mission system or mission or environment, I should say, along with the all what we have developed with the software and in an integrated way. And this is not a one-time process. It can be, because of this virtual platform, virtual environment, we can always iterate this design process to make a corrective action and improvise this, again. So I did not show many of the environmental and weather conditions, like a what will happen, like if it is having a the very high speed wind, or you have a rain, you have a different sun position, which I did not mention, but those are the all things can be created in those the mission environment, and model those environment and perform this still a digital way to perform this mission, and making sure that it is a reliable and safer operation from the not only development but also from the operational perspective. So with that, let me I'd like to thank you everyone for your attention, and we'd like to conclude, and if there is any questions, I'm ready to answer. Okay, so there was a question which is coming as regarding the validity of simulation, as into what extent has been substantiated with the practical flight path and extent of input from SMEs, that is of operators. I don't know. I didn't understand that full question, but let me just. But what actually, if I understood correctly, what you were trying to ask, that whether validation of the the simulation results to the reality. So in the operational environment, as I said, this is a there are two types of the validation. One is that product, the label itself, and the second is its operational validity. So right now what I showed is more from the operational validity, and these are well validated. There are various different companies are already using this tool. So you understand that you are developing the mission path or the flight path, and then you are trying to operate and validate. So there is a not very specific error is like what you were designing the path, right? So that designing the flight path or the mission path is the actually engineers the data. So so that's a so there's nothing to especially to validate from the path generation perspective. Once path is generated, what we are doing is just trying to run those the platform along those path and see the operations of the sensors which we have installed on the aircraft and also on the ground control station, and see that whether those are meeting those specific requirement from both from the sensor side or maybe from the software operation side. So these are well validated. Maybe if you are interested in, please get in touch with any of the ANSYS team, or maybe you can drop a note to me. We can share. Even in the ANSYS website, there is a lot of customer references or the validation cases will be available for you to refer. But on the product wise, developing like a durability or a software validation. So what we are saying is the software is exactly the same software which actually will be operating into the flight. So this software, exactly the same software. So there's no difference between the software which has been used into the simulation and the software which you are going to actually place onto your aircraft. So it's the same software. So if software is validated by itself, you are using the same software to mimic this mission verification for operational analysis. I hope I able to meet your expectations on this question, but if not, we can take it offline as well. Any other questions? Okay, let me also see.
Yes, sir. Thanks. Thank you, sir. You can have a conclude remarks and we can close, sir. If there is no more questions, you can give a conclude remarks and you can close, sir.
Okay, so yeah, so there's the only one question I had received. Just let me check into this. Otherwise, last one. Okay, so I think, yeah, we will just go ahead with we'll conclude this, I think, the session, and thank you, everyone. I think there's no question further. So let me conclude this session, and thank you very much for your attention and participation. Have a good day.